Welcome to the training webinar on gamma ray spectrometry basics. We will slowly get started as it is now 9 o'clock in Austria, where I'm located. I do see that we have still some people joining in, probably doing the whole WebEx registration and logging into that. But we'll start to go through some of the practical details about this webinar. So first of all, this whole session is being recorded. It means that for those who are not able to watch this live, then you are able to watch it later on whenever it suits you. And you can also feel free, of course, to share the video with any colleagues of yours who would have been interested to join but weren't able to. So it's being recorded. The slides for this lecture, as well as the exercises which are related to this lecture, are already available for download from Dropbox. And in WebEx, in the chat box, you will find the link to this Dropbox where you can download those files. This is a large webinar. We have really several hundred people who originally registered. We'll see how many people eventually join. This means that we have to be a little bit strict, and we cannot allow everyone to enable their microphones and so on as they wish. So if you have a question, you'll have to do that by writing the question, and there's a special Q&A panel in WebEx where you can ask your questions. And then at the end, after the lecture, we'll take a look through those questions, and I'll really try to answer as many of those as I can. So I expect we will spend really a maximum of 2 hours together today. And again, to those who just joined, hello, welcome to the webinar. Good morning if you're in Europe like me, maybe good afternoon or good evening or even good night, depending on where in the world you are. I hope you will find this webinar useful and interesting, and I think we can get started. So this is the first webinar in a session of 3 planned webinars that are organized within the framework of the IAEA's network for analytical laboratories for the measurement of environmental radioactivity. So that's the ALMERA network, and you'll see the logo here in the top left corner. Originally, this webinar was supposed to be organized only for ALMERA laboratories, but when we saw the huge interest, we decided to open it up more generally. And I think now there are around 50-50 people who are working in laboratories who are members of this, and 50% that work in other laboratories. So if you're not familiar with that network, if you Google IAEA ALMERA, you'll find some nice information about that. As I mentioned, this is the first in a session of 3 planned webinars that will be running this spring period. And the topic for today's webinar is gamma ray spectrometry basics. My name is Alexander Mauring, and I work as a gamma spectrometry specialist at the IAEA's Terrestrial Environment Laboratory, and that's located in Seibersdorf, just outside of Vienna in Austria. And you'll see my information there on the page. Fortunately, I'm not alone today. I also have my colleague Alex Twinkle working behind the scenes to make sure the whole technical part runs smoothly. And thanks, Alex, for helping with this. So, of course, this is a big webinar, and it's a huge help to have more people involved to organize it. So let's go to the contents of today's lecture. So this is gamma ray spectrometry basics, and I think most of you have already seen the invitation, which had the kind of content already outlined. So there will be no surprises here, hopefully. So we'll start a little bit about introducing what is actually gamma ray spectrometry. We will go through some theory on decay, on photon interactions with matter. We'll see how that relates to the main features of the gamma spectrum. We'll go through some of the different detector types and their properties, especially some focus on high purity germanium detectors. Then we'll see how the detector and other components come together to make a measurement system. And we'll also discuss how do we do a so-called energy calibration of this system, which is necessary to be able to use this measurement technique, gamma ray spectrometry, to perform identification of radionuclides. And then finally, we'll summarize everything or summarize the main parts by looking at an overview of a typical measurement process, how that might look. So I've decided to highlight the basics here. This is a basic level training. I see some names that I know are definitely not newcomers in this field, some people who have very long experience. And maybe you will still learn something new here, or maybe it will be useful repetition of things you learned a long time ago. This will be a basic level training. We will not go deep into the physics of anything. We will keep it quite general so that hopefully most people, even those who don't have such a technical background, can keep track and kind of follow the lecture. So I hope that will be fine, and I hope you'll find it useful and interesting to your work. And with that, let's go ahead. So what is gamma ray spectrometry? So very, very basically, it's a measurement technique for the identification and quantification of gamma ray emitting radionuclides. And usually what you are doing is you're measuring some kind of sample to see, okay, what is the radionuclide content in this sample? So this is something which you can do in the lab, as illustrated here on the left. It's also something which you may do in the field, or in situ, as you call it. So both are kind of versions of gamma ray spectrometry. However, whereas in the lab, you might take a sample from somewhere and bring it to the detector, if you do it in the field, of course, you're doing the opposite. You're taking the detector and kind of bringing it out to the sample or to the field where you want to do a measurement. On this picture here, the actual detector is hidden within this lead shielding that you'll see here, kind of bluish. But if you had, let's say, supervision and can look inside here, it might look something like this. You have a detector inside here and maybe a sample which you are measuring on that detector. So that's how that might look. So the sample is here packed in a plastic bag so that it doesn't contaminate our detector. Whereas in the field, you might have really something very large, so the sample might really be this field that I'm standing on here in this very picturesque part of Sweden, where I was lucky enough to go for an exercise a couple of years ago. So that's kind of what gamma ray spectrometry is in terms of the general technique. But of course, what we actually look at is this, what is very small here on the computer, the spectrum. So it's also about looking at this kind of spectrum output that you will get from the measurement and using it to say something about the radionuclide content of what you are measuring. Which radionuclides are present there and how much activity of each, so how many becquerels. The spectrum itself is a plot, or it's an energy spectrum, but basically what it is, it's a histogram plot of photon energy events in our detector that we register each event as a count, and eventually what you will see are several peaks that appear in the spectrum, where you will use those to tell you exactly which radionuclides and how much activity is present there of each. So this is actually a lot of the job in gamma ray spectrometry, is about looking at this spectrum and trying to get some useful information from that. So we're talking here about radionuclides. So I thought it would be fitting to kind of jump back a little bit to what are radionuclides. And I will show you something now which I think a lot of people have seen during their studies or during their work or whatever. This is the chart of the nuclides in hopefully the latest version. Maybe one or two small things changed since then. This is basically each tiny square on this plot here, which is a plot of different kind of variations of elements with neutron number on the x-axis here and atomic number on the y-axis. Basically each tiny square shows one possible configuration of protons and neutrons in an atomic nucleus that have been observed so far. So there's around 3,000 of those. So don't worry if you can't read the tiny text on those, because there's really a lot. And of these 3,000, actually only around 250 are stable. That means not radioactive. And the rest actually are some kind of radioactive. They are so-called radionuclides. So a nuclide is kind of refers to one specific combination of protons and neutrons. For example, this tiny square here. And then radionuclides is simply a nuclide which is radioactive, which, as we see, really refers to most of the possible variations that we have here. Now, there are several modes on how a radionuclide will decay in order to eventually become something stable. And you'll see the main processes here. I'm not going to go through each one. I have a source here which you can visit with a link at the bottom here. You can visit that if you're interested in more. We are primarily interested in this kind of gamma decay, which happens when a nucleus in an excited nuclear state emits this energy that it's excited by to get to a less excited state, let's say, and eventually through maybe several decay processes to reach something which is really stable and doesn't undergo any further radioactive decay. There's also the other usual things like alpha decay, beta decay, positron emission, electron capture. You'll see a bit of the details here, like nuclear equations, and also what happens to the mass and atomic numbers as a result of that specific decay process. Interesting to note, the gamma decay doesn't change the mass, and it also doesn't change the atomic number. So there's no difference in mass and no difference in charge. Otherwise, I don't want to spend too much time on this. We're interested in the gamma decay. So let's go for some quick facts about gamma decay. So gamma decay, what this is kind of an emission of pure electromagnetic energy, as we said, with zero mass and zero charge. This is not something which generally happens alone, but it usually happens after an other decay process, which leaves the nucleus in an excited state. So maybe already the radioactive element emitted an alpha particle, but it still has some excess energy that it needs to get rid of. It will send out that energy as a gamma ray. And what is so nice about this, because of the wonders of quantum physics, is that the energy at which this radiation is emitted, so the energy of the gamma ray, it cannot be any value, but it's very strictly defined by the so-called decay scheme of a radionuclide. And since the energies are so strictly defined, in many cases, a certain energy or a certain set of energies might be unique to the radionuclide of interest. In that sense, we might say it's kind of a fingerprint for that radionuclide with which we can make a sure identification. Here is kind of a general picture of what's so-called decay scheme might look like. And on the next slide, we will look a little bit closer at a specific nuclide. This is the nuclide yttrium-88, which decays by the electron capture process down to strontium-88. However, on the way, it will decay by electron capture to one of these excited energy states. So what we're looking at here the higher up we are in this figure, the higher the kind of energy of that state of the nucleus. So we have here a couple of excited energy levels, and if it decays to a certain energy level, it would like to reach the zero level, the stable level, and it does that by emitting gamma ray photons in order to get rid of that energy and eventually reach that stable state with no excess energy. And as it does that, the emitted gamma ray energies approximately correspond, or very closely I would say, correspond to the energy difference between the level it goes from to the level it goes to. So for our example of yttrium here, let's say we have a decay down to the level 2 here, and it emits the 2 photons, gamma ray photons. If we were to make a spectrum of an yttrium source, exactly like we would expect, we find in the spectrum 2 nice clear peaks, one at around 900 kilo electron volts, which is the unit at which we measure these energies. That corresponds to this transition here between these two levels, the level 2 to the level 1. And there's another peak here at around 1836 kilo electron volts. That corresponds exactly here to this transition, which goes from the energy level of 1836 to 0, the difference of which, of course, would be 1836. So we get this corresponding full energy peaks, indicating that the energy that was emitted as a gamma ray it hit our detector, the whole energy was deposited there, and we get signals to these peaks as we count that over a certain amount of time. We'll go through a little bit more in detail exactly the mechanisms for this, because as you can see in this spectrum, there is not just 2 peaks, there is a lot of other things as well happening, but don't worry, we'll come back to that. What I would like to go to first, though, is something which I think a lot of us maybe take for granted, but it's not so often defined, because some people call this gamma ray spectroscopy, and some people call this gamma ray spectrometry. I call it spectrometry, and here's my reasoning for it. To me, gamma ray spectroscopy, this is kind of spectroscopy is kind of the general study of radiated energy in spectrum format. So kind of like a general science, but maybe not too specific. However, spectrometry, this metri that this word ends with, this actually means something about measurement, calculating something. This is using the spectrum then to calculate actual quantitative results. So from this spectrum, our detective here might finally reach his conclusion and say, Eureka, here we have 1000 becquerel of cesium-137. And to me, that is kind of the difference between spectroscopy and spectrometry. And I usually like to call it spectrometry. If you're very used to call it spectroscopy, I will not hold that against you. Please continue with that. But if you're wondering why I constantly say spectrometry, this is why. So this is a technique which has really quite a lot of applications. And here is just a small list of those and some pictures to show some of the strange and interesting things you can do using this technique. So you can use it for environmental radioactivity monitoring. It's used in environmental preparedness, radiation protection, nuclear security and safety, such as, for example, border control. You can also use it for larger kind of particle physics experiments. You use it in geo and astrophysics, for example, to look at cosmic radiation. You can use it as a part of medical isotope production, many, many more things. So there's really a big field of application for this. And I see from the number of participants we have to this this webinar that this is a field which has really huge interests out there all over the world. So that's really cool to see. This is an Almera organized webinar. So you'll see a lot of my examples will maybe be kind of focused towards these 2 first things here, especially related to environmental monitoring, which is kind of the specific topic of Almera. However, the physics behind is of course the same no matter which application you're using it for. So even if the example is maybe not exactly in your application, I hope you will find some use of the theory behind. Here are some typical radionuclides which might be of interest, especially for environmental monitoring, emergency preparedness, and so on. I split them into kind of two categories. They are anthropogenic radionuclides, kind of those which are man-made. They are here because of something that humans have done, such as nuclear energy production or something like that. And natural. So these are nuclides that kind of would be there even if we didn't do anything, but some of them might be present in higher quantities because of industrial things, for example. I think if you're used to gamma spectrometry, you will see a lot of known radionuclides here. So you'll see the radionuclide here. Some are kind of in pairs because you rarely find one without the other. And here you have kind of the main characteristic gamma energies that we would like to find in our spectrum then as a peak. Yeah, so you see the different nuclides, the different energies they emit, the anthropogenic ones and the natural ones. For the natural ones, there's a star next to some of these energies, and that indicates that the energy doesn't actually come from what I've written as the radionuclide. It comes from a daughter radionuclide, but usually you will find those always together, so that's why I write it like that. If that doesn't make sense to you, I think don't worry about it. These are basically the nuclides and energies which you a lot of the time might encounter in some applications of gamma spectrometry, especially the natural ones which are present, yeah, a lot of places. So those are just some examples. Again, the gamma spectrum, as we said, the location or energy of the peaks, if we plot it here as an energy versus counts spectrum plot, it tells us which nuclide or which nuclides are present in the spectrum of what we are measuring. And the size of the peaks will tell us something about the nuclide activity. Of course, this being radioactivity, which is a process that happens over time, of course, the longer you measure, the larger your spectrum will become, the more counts you will have in your peak. So this is the size acquired in a certain time that we're talking about here. In order to kind of do this part, to calculate the activity of the nuclide of interest, you will need to do something called efficiency calibration, which we will talk a little bit about today, but not much. But in the webinar series, the third session will be solely about how do we calibrate our detectors to get good results when we try to estimate activities. So if you're interested in that part, I really recommend you to join that webinar also, which I believe will be on the 5th of May. As we also mentioned, it's not just the normal peaks that we expected. This was also the yttrium spectrum, so we saw the same peaks like we took a look at before. There's also many other effects. So some of them you will see here, such things as Compton continuum, escape peaks, pile-up, backscatter, a lot of things which maybe sound a bit foreign and you don't really know what it means. So I would like to explain that a little bit about that to you. And in order to see where these come from, we should look a little bit about gamma photons and how they actually interact with our detector to produce a signal there, which eventually over time many signals will build into a spectrum. So let's start with that. Let's look at first also something which many people might find quite familiar. This is the electromagnetic spectrum. So this basically shows different type of electromagnetic radiation sorted by kind of the frequency or wavelength. So at the right-hand side, we have the smaller wavelength, but higher frequency radiations. and then at the left side is kind of your low frequency, long wavelength waves. So you'll see here kind of what the size of the different ones compare to. We're of course interested maybe in this right-hand part of this spectrum, of which visible light is also somewhere here in the middle. But with gamma rays, we're quite far away from that again in the extreme high frequency part of the electromagnetic spectrum. So gamma rays have frequencies of more than 10 to the power of 19 hertz. So that's oscillations per second. This corresponds to a wavelength of less than 100 picometers. The order of magnitude of this, so the distance between two waves would be kind of on the order of magnitude of a typical atomic nucleus. So this is really tiny. If we look at that in terms of energy, we find that gamma rays have photon energies which start at around 40 kilo electron volts or so. It's not a hard cutoff, but this is approximately where we start to find our gamma rays in the spectrum. Kilo electron volt is also a measure of energy. Some I don't know, thermodynamic physicists might be more familiar with the joule, but since this corresponds to like 10 to the minus 14 joule, you'll understand why we use kilo electron volt instead, because it would be very impractical to have such tiny numbers for our energies all the time. And remember, for all these types of electromagnetic radiations, and also then including gamma rays, there is no mass and there is no charge. So the question then becomes, okay, how do you stop a gamma photon? Because compared to an alpha particle, which consists of 2 protons and 2 neutrons, or a beta particle, which can be an electron and positron, those two have a mass, they have a charge, which means that there can happen some collisions, really, some proper collisions when they try to go through different material. Indeed, if you're familiar with these types of radiations, you'll know that alpha radiation can be stopped really by a thin sheet of normal paper, whereas beta radiation will pass through that generally, but can be stopped with a thin sheet of aluminum. However, for gamma radiation, it will usually not be stopped by these things, and you will need something like a thick block of lead or so to even be able to stop it. And even then, there's a probability that it might pass through, because photons do not have a fixed stopping distance. And instead, we need to look at the probability of interaction. So it's the statistical thing we have to look at. What is the probability that our gamma photon at a certain energy will be able to pass through a material or not? So we call this photon attenuation. So attenuation means like dampening or lessening. And let's say we have a photon beam here on the left side of our slide, and we're shooting photons all with the same energy through some material here with a thickness of x and a so-called linear attenuation coefficient, which says something about how efficient does this material stop photons at that energy. And generally heavier elements and higher density materials will have higher linear attenuation coefficients. What we can do is we can shoot kind of have a certain intensity of incoming photons here on the left side. Then we pass it through our material with a certain thickness, certain attenuation property. And then we look on the other side, okay, how many of our photons made it through now? And actually, if you were to look at many different thicknesses of the material, you could make such a nice plot. You would see that that the intensity of the photon beam decreases exponentially with the thickness of the material. And that can be expressed then with an equation of this form, the so-called Beer-Lambert law of attenuation, where we use that then to plot the curve of the photon beam intensity as a function of distance in the material. Of course, if the attenuation is higher, this will drop off more steeply. but it will follow this exponential relationship in some form, for any material, basically. So that's kind of general about photon attenuation, explained very simply. So if there is any advanced physicists here, I'm sorry for simplifying it so much, but that's kind of the basic idea of it. And the other idea that I want to mention is that what happens in the material can actually be one of several different things. There are several ways, several interaction mechanisms for how the incoming photon, any incoming photon, may interact with the kind of atoms in the material or particles in the material that it's passing through. They are listed here. So it's the photoelectric effect, the Compton scattering, and so-called pair production. And we'll look into each one in a little bit more detail now to kind of see, okay, what's happening here and maybe what is the effect of that potentially on our gamma spectrum. So we'll start with the photoelectric effect. And the photoelectric effect is when the entire energy of an incoming photon, in this case we are talking about the gamma ray photon, is transferred to what we assume is an inner shell primary electron in the detector material. So let's say we have an atom here, and I know this is a hugely simplified model of how the atom looks, and really this is not completely true, but you still see this kind of planet system model of the atom a lot of places, so I hope it's acceptable to show it in this way. Basically we have the photon coming in, and we usually express the photon by this kind of squiggly line here. It comes in, it transfers its energy over to an electron, knocking it loose from its orbit around the nucleus. And that electron has quite a high energy then, quite a high velocity, and it will have the possibility, as it's slowing down in the material, to produce many secondary electrons. So don't get tricked to think that there's just one electron going around here with all that energy. There's actually going to be many electrons produced from one photon interaction. Don't want to go so much into more of the physics there. What's important there is that kind of the energy that is absorbed in our detector material is really the whole energy of the incoming gamma ray photon. The full energy of the photon is absorbed, and this is important because since the whole energy is absorbed, that's when we can get a count in our full energy peak of the gamma spectrum. And that's really what we want. We want a lot of counts in our peak and not a lot of counts randomly around the spectrum where we cannot really use it to do any calculations later on. So that's the photoelectric effect, giving us counts to our full energy peak. We like this effect. Then we have the Compton scattering, in which there's also an interaction between the photon where it transfers energy to an electron. However, we assume this electron to not be so tightly bound, and the whole energy is not absorbed. So we do have one electron, which some of the energy gets transferred to. However, we will also have the emission of a new kind of photon, if we can call this a gamma ray. It's a bit questionable, but it's a new photon here with slightly less energy. So you see the energy of our original photon is transferred to the electron and to another emission of another photon. So this leftover energy, let's say, this energy which goes to the new photon, this may go on to interact further in our detector. And if in the end the whole energy is absorbed, then great. However, if that photon then manages to escape our detector without depositing its energy there, then we will not get a count in our full energy peak. We will get instead a count to our Compton continuum. And this we will see in a few slides how it looks. This is actually not a single energy, it's rather a range of energies with a little bit different probabilities depending on the energy. And that's actually controlled by these equations here, which I will show you for your interest, but I will not go through or make any kind of derivation of those. What's important to note is that the energy deposited or energy given over to the electron, which then will be absorbed in the detector material, has a maximum. The maximum happens when the scattering angle of here is equal to 180 degrees. And this is the maximum energy, and we will see the so-called Compton edge corresponding to this energy in our spectrum from a given incoming photon with a certain energy. So we will see again in a few slides how that looks. First, however, I would like to show the last effect that for how a photon might interact in the material, and that's the so-called pair production effect. So in this case, incoming gamma ray photon entering the detector will make a very wonderful interaction, kind of close to a nuclear field of an atom. It will prove kind of Einstein's principle in practice that E equals mc squared, because it will convert the energy over to mass. So it will produce a so-called electron-positron pair. And there's a kind of minimum required energy to do this, which corresponds to the rest mass energies of this electron-positron pair, which is 1022 kilo electron volts. If the energy of the incoming gamma photon is less than that, then it doesn't have enough energy to for the pair production, doesn't have enough energy to produce these particles. So the photon comes in, this process happens, an electron is sent out in one direction, that electron will transfer its whole energy to the detector. Then there's a positron also emitted. So positrons, being the kind of evil twin of the electron, will eventually slow down and eventually meet another electron. So it will maybe move some randomly around in the detector. It will meet an electron. Electron plus positron will annihilate. So we have the opposite reaction. Instead of energy becoming mass, as we have at the start, we have now mass becoming into energy. And again, we have this these rest mass energies, so 511 keV on each side. You sum those up, you'll see it equals 1022 keV. So two 511 keV annihilation photons will be created from this process. Now, these being photons, again, they don't have a fixed stopping distance. There might be the case that one of them or both of them escape the detector before they deposit the energy there. In that case, we will have like a budget deficit for our energy budget in the detector. So the signal we will get, which will later become a count in the spectrum, might be kind of the original energy of the incoming gamma ray photon minus 511 kilo electron volt in case where one of the annihilation photon escapes. Or in the case where both of them escape, of course, the deficit is even bigger. We will get a count at the energy minus 1022 kilo electron volts. And this is what we call the so-called escape peaks in the spectrum. So you might sometimes have peaks which don't really correspond to the decay scheme of a nuclide, but rather to the decay scheme energies minus these 511 or 1022 keV. So that was very briefly about the interaction mechanisms. And if you're more interested in that, I think there is an endless array of textbooks that explains the physics of this in a lot more detail. So I don't want to take the time on that now. Important to note, and even if you fell off a little bit, my explanation is that due to the different photon interaction mechanisms, the spectrum doesn't give us a perfect picture of the decay of the nuclide. Indeed, if we just look at the different possible interaction mechanisms, the mechanisms with which the gamma ray photon deposits energy in the detector by interacting there, the photoelectric effect, Compton scattering, and pair production can give signals to different parts of the spectrum. Of course, you might have the case where first there is Compton scattering and then the kind of leftover photon energy is absorbed by the photoelectric effect. It's also possible. Combination of effects can really give a signal anywhere. But just to compare, like what you might expect from the decay scheme, maybe you expect kind of just like one single very sharply defined energy emission. However, what you might see is something like this, the spectrum. So it's really a spectrum, a range of energies, not just the single peak at the energy we would expect from the decay scheme. The three main kind of interaction mechanisms, there are some less likely ones as well, but I won't mention them here because they don't really give big effects to our spectrum. The three main interaction processes, they have different probabilities for how they interact depending on the energy of the incoming gamma ray and also depending on the atomic number of the absorber. So on the left side you'll see a plot of kind of on the y-axis is the atomic number of the absorber, and on the x-axis is the energy. And then you'll see kind of for a given atomic number, so I made a red line here for germanium, which would be the case for high purity germanium detectors. You will see that for up until kind of a bit above 0.1 MeV, mega electron volts, so that's around 100 kilo electron volts. The photoelectric effect will be dominant. Really, then there is from around 100 keV up to around almost 10 MeV, or let's say 8 or so, which is around 8,000 keV. So this is really most of our spectrum here now, because a typical spectrum maybe looks up until just around 3 keV or 3 MeV, sorry, or so. We see that for germanium, the Compton effect is dominant really for the major part of the typical photon energies that we will expect from our gamma rays. And then for really higher energies, the pair production effect can become dominant. And you see as you kind of increase the atomic number of the absorber that the photoelectric effect becomes more dominant for the lower energies, and the pair production effect becomes more dominant for the higher energies, and the area with which the Compton effect is dominant is smaller. Looking more specifically at the germanium detector, we will see also this energy dependence. So we see again kind of three different curves for the Compton effect, for the photoelectric effect, and for the pair production effect. These are kind of their relative probabilities, which all build into the total probability of interaction. So you can see again that for the low gamma ray energies, that the curve, the total curve is dominated by the photoelectric effect. For a kind of more medium range energies, the Compton effect is the dominant effect. And as you go really high in energy, the pair production effect becomes more dominant. For all practical purposes, in normal gamma ray spectrometry, usually the photoelectric effect and the Compton effect will be the dominant ones. However, pair production can always still occur statistically as long as the energy is then higher than the threshold of 1022 keV. So that's why you'll see like below 1000 and a little bit, there is basically zero probability for the pair production effect. So we talked about the main mechanisms which produce effects in our spectrum. There are also some other effects that may contribute. So there can also be, of course, interactions happening not in the detector, but in the materials around the detector. But then kind of the leftover radiation is then sent out back towards the detector. That's when you'll have such things as backscatter and annihilation photons and so on. There's also kind of summing effects that can happen, which will not go into detail here, but there is kind of true coincidence summing, random summing, basically when more than one photon interacts with the detector in such a short a time that the detector interprets that as just one big signal. So we'll get some kind of summing there, which can pile up at the higher end of the spectrum or create some other effects. There's also peaks that are not related to gamma rays, but rather to X-rays. So both of those are types of photons, but don't fall in the trap of thinking they are the same thing, just different energies. The production mechanism for X-rays, they are emitted by the reorganization of electrons which are around the nucleus, whereas gamma rays are actually photons emitted from the nucleus itself. So that's a big difference in how they are produced, even though they are both kind of in our electromagnetic spectrum. So, wow, that was a lot of theory about photon interactions. Now, let's see how can this kind of translate into some actual spectra. So here is a typical spectrum from a cesium-137 source. So cesium-137 has a single kind of primary gamma ray emission at 661.6 kiloelectron volts. And you'll see here in the spectrum, you get indeed one peak at that energy in the spectrum. And then you have kind of this kind of Compton continuum you will see here. You will see some kind of an edge here. I hope you can see my cursor. You will see this edge corresponding to this maximum Compton edge energy that was shown in an equation a few slides ago. That will usually not show up as like a nice peak, but rather as like an edge. Of course, if there's kind of multiple Compton processes happening that each deposit a little bit energy, you might get something in between here. You have sometimes again when photons sum up, and you'll have signals even above the energy of the full energy peak because of summing of signals there. So that's kind of a pulse pileup you'll see there. There's some backscatter radiation, which you'll see from interactions of gamma rays with the materials around the detector. Yeah, so this is still kind of like a basic spectrum. You have several effects, but there's still just kind of one peak. And of course, the energy of the cesium-137 is less than 1022 kiloelectron volts, not enough to have any kind of pair production here. Now let's look at another single gamma emitter with a higher energy. So this is aluminum-28, also a radionuclide, which emits one single gamma ray at around 1,1778.9 kiloelectron volts. This now is above this famous threshold for the pair production effect. So in addition to kind of these Compton edges, the full energy peak, the pileup, you now have these escape peaks, which you'll see here. So there's a single escape, which is kind of exactly 511 keV below the full energy peak, where one of the annihilation photons escaped our detector before it deposited this energy there. There's also this double escape peak, exactly 1022 kiloelectron volts below the full energy peak. Because there's pair production, there is kind of positrons being produced, and they are annihilating with electrons. And sometimes you just get a signal from the annihilation peak. This particularly happens if the original pair production interaction happened in the detector shielding, for example, and you get this annihilation photon sent out towards the detector, and it registers there. So that's how a typical spectrum could look from a single gamma ray emitter with energy high enough to have this pair production process take place. Of course, actual gamma spectra, you usually won't just be looking at one single nuclide, and actual gamma spectra then are a combination of effects from different radionuclides. Let's say you're measuring a sample or a source which is a combination of cesium and cobalt-57. Of course, you would expect then the spectrum to be a combination of all the peaks of all the nuclides that you are looking at. So it has this has now both the cesium peak as well as the two cobalt-57 peaks represented in the spectrum. And some spectra have few nuclides and a few peaks. Some spectra have a lot of nuclides and a lot of peaks. This is an example of a a spectrum which was taken from a norm sample. So norm is a naturally occurring radioactive material. And we saw towards the beginning of the lecture some examples of which nuclides those are and some of the energies. Actually, that was a simplified picture. There's a lot of energy emissions associated with such samples because there's usually several nuclides present at the same time, and each nuclide sends out many gamma rays. So you might end up with something like this. This is again a spectrum, but this spectrum has more than 100 different peaks because of the combination of nuclides in the sample that I measured here. And that's why a lot of the art of gamma spectrometry is how do you then make sense of this? It can be quite complicated, but it's really possible to get useful information out of it if you make the right steps. So that was a lot about the spectrum and how the spectrum kind of is built up and the different things you might see there. Now, let's look at kind of the measurement system more generally. And this is kind of the basic components of the measurement system. So let's say I have some kind of a sample here, which has some radionuclides in it. It's emitting gamma rays, some of which hit my detector. This being a high purity germanium type of detector, which is cooled, so that it has some kind of a cooling system here below it. There's a preamplifier connected to that. Basically, you have your detector there. You have some kind of electronics. Traditionally, you had this kind of rectangular NIM, nuclear instrument module electronics. Nowadays, more common to have kind of a digital analyzer, which is often a lot easier to work with. And then, of course, at the other end, you have a computer with a software which you use to kind of control the detector acquisition, to view the spectrum, to do the analysis, and everything like that. And of course, sitting here and making sense of this is the analyst, which I guess might be a lot of you guys. So this is very kind of basically how a typical measurement system for the measurement of gamma radiation might be. It might not look exactly like this depending on your detector and your application, but certainly kind of these components will be more or less the same. So we'll go in a little bit of detail about each type now. And we will divide the two main types of detectors that are used for gamma ray spectrometry into scintillation detectors based on scintillation principle. So it's a crystal which emits light when photon energy is absorbed in it. And you'll see some typical configurations here, such as sodium iodide, lanthanum bromide, cerium bromide, cesium iodide, and so on. Then you have the semiconductor type detector, which has another detection principle, which we'll go into a little bit later. And it has different possibilities, such as high purity germanium, silicon, cadmium zinc telluride, I guess are the main ones. This what you see here would be a typical example of a side-facing high purity germanium detector. Some quick kind of pros and cons, advantages and disadvantages of the different types of detectors. So the scintillation detectors, such as sodium iodide and lanthanum bromide, they are relatively low cost. You can make them into large sizes. Of course, if you have a large detector, there's a high probability then that the photons will interact in there. They have fast signal processing. They are generally more robust. On the downside, they have quite bad peak resolution. If you're with lanthanum bromide, those have some internal contamination, which can be inconvenient. There's also occasionally kind of temperature instability associated with these systems, though I know newer systems have some compensation for that. So those are some pros and cons of the scintillation type detectors. Now for the semiconductor detectors, such as high purity germanium, usually you'll find that the peak resolution is superior, and these kind of systems usually have a very nice and low limit of detection. So that means like being able to measure small activity levels in samples. So low is good. You would like your limit of detection to be low. That means you can detect low levels of radioactivity. Some disadvantages of the high purity germanium detector is that they can be very expensive, I would say, depending on your detector system. You can only make them up to a certain size, though later years quite large sizes were able to be produced of germanium. They require cooling, that's especially for high purity germanium, and they are relatively fragile. So if you look at just like the number of pros and cons, you might think, oh, this high purity germanium doesn't have so many advantages. But actually this peak resolution thing is so important, and we will see now why the high purity germanium detector is really considered the gold standard of gamma ray spectrometry measurements. In order to look at resolution, we need to define one concept, and this is the full width at the half maximum. This is how you measure the resolution or a sharpness of the peak. So let's say we have one peak in the spectrum, which looks something like this. So we make it kind of approximated by a Gaussian shape. And we look at kind of the height of this peak, its amplitude from the baseline of the spectrum all the way up to the maximum. And then we look at what is the half of the max. And then at the half of the max, what is the width of the peak? This is the full width, so the full width at the half max. And why is this so important? Well, it kind of makes sense that when you are looking at peaks in a spectrum, and especially if you have many peaks, you would like to be able to separate them. And actually, you'll see that peaks that are less than one full width half maximum value apart will be extremely hard to separate from each other, even using software. So this is kind of the definition of the full width at half maximum. Again, a parameter that you would like to be low, you would like it to be small. That means that the resolution is good. You have very narrow, nice peaks. Let's look at a comparison of the same sample spectrum on three different detector types. So here you have kind of the same spectrum or the same sample measured on a high purity germanium detector, which is blue, on a lanthanum bromide detector, which is the red one, and the sodium iodide detector, which is the green one. And here you can really see that on the high purity germanium detector spectrum, you can see a lot of peaks, some of which are close to each other, which on the worse resolution detectors get joined together and they get swallowed up by other peaks next to them, and you basically lose a lot of information about the individual peaks. And on the sodium iodide, you only see really a few peaks in the end in the spectrum, where in the germanium detector you saw several dozen peaks. So this is part of the reason why really we generally go for the high purity germanium detector for the precise measurements by gamma ray spectrometry. And if you look relatively, kind of at the peak at 662 keV, at the relative full width half max, so what is the width of the peak compared to its energy? We'll see that for high purity germanium, it's around 0.2%. So the full width at half max is around 1.5 kilo electron volt. For lanthanum bromide, it's around 3%. And for sodium iodide, it's around 7%. So that is quite drastically different values, and that's why the peak is so much wider on the scintillation type detectors as on the high purity germanium detector. There is also an energy effect, so peaks at higher energies will tend to be wider than at low energies. I will not go through so much why this is. It has to do with something about what kind of noise effects contribute to the resolution, but also good to know that you might have a very small resolution at the low energies and then quite a bit larger one at the higher energies. So for the remainder of this presentation, considering that high purity germanium is the golden standard here, as we have just demonstrated why, we will focus on those types of detectors now for a bit. And also because these are the most commonly used type of detector in Almera laboratories. So let's look at the high purity germanium detector. Sorry. So the high purity germanium detector itself is basically, can be looked at as a diode with a PIN structure, which is connected to a FET assembly. This is how you'll see it like defined. If you looked in the dictionary, it might not make sense to you so much, but the detection principle is actually not so complicated. You dope the crystal with some impurity atoms to increase the conductivity, and then you make it into some kind of a crystal. And here you'll see some typical crystal shapes. So this would, and often you'll see this kind of coaxial shapes. So it's a cylindrical, this is kind of like a cross-sectional view of different types of crystal configurations. And you'll see that for these coaxial ones, there is like a hole in the middle. And that's because due to the way they work, you can't really make it into a perfect cylinder. It would be very inefficient to collect the charge which is produced then. So that's why you go for these coaxial things. And generally you have two electrical contacts. So you might have one type of electrical contact on kind of the outside here. This is a p-type coaxial detector. So this is an N diffused contact. And then you have a P implanted contact on the inside. And on the opposite side, you might have your N-type detector, which has, it's kind of the reverse, the electrodes are reversed. So you have the P contact on the outside, the N contact on the inside. And we'll see in a couple of slides what this can mean in terms of, for example, the detection efficiency at low energies, because since this contact layer is thinner for the N-type, you have a better chance for detection of low energies as they don't interact in the contact, they interact in the active volume. So we would like to have interactions in our active volume here of the crystal. There's also some other types of crystals. You might have a well-type detector where you kind of flip the detector on its head almost, not exactly, but almost, and then you can fit your sample here into the well. So you have kind of the detector surrounding the sample, which can be quite nice when you're trying to measure low activities. There's also planar detectors, which have more like a, I don't know, flat shape, thinner shape, used for low energy applications, for example. And yeah, there are other types as well, but these are maybe some of the more common crystal configurations, with the definitely most common being these coaxial types, p-type or n-type. Then what you'll have is that you'll mount your crystal into a vacuum housing with a holder, and there'll be vacuum in here to kind of keep the crystal completely isolated from the environment, also for thermal conductivity to reduce that. And then you have this end cap around to protect the detector. So when you are looking at the detector from outside, you never actually see the crystal. You see the end cap. That's usually like an aluminum cylinder looking thing. Though nowadays you see more and more where the top of the detector, where you might place your sample, is replaced, and instead of aluminum it might be something like carbon fiber. Carbon fiber, having a lower atomic number and lower density than aluminium, has better transmission than for low energies of gamma rays to reach into our detector. So the high purity germanium is one of the purest materials in the world. It's grown only in some couple of very special factories around the world. And on the left side, you'll see a picture of how can this crystal growth process look. And on the right side, you see kind of the intrinsic crystal structure of the germanium atoms that is achieved in the crystal. Germanium being a semiconductor, where the valence band of the atoms in the crystal being a suitable gap away from the conduction bands in which the electrons are allowed to move around in the crystal material. I've included some links here if you want to read more about this, and also read more about kind of the semiconductor physics behind. We will kind of take it for granted that this detector is existing. And we will look now at kind of what happens when the photon interacts in there. The detection principle of a high purity germanium detector, if we consider this PIN structure, so you have a P contact on one side and N contact on another side, and then this sensitive intrinsic region in the middle, is that we first of all need to apply a reverse high voltage bias, so opposite of what the contact might suggest, of several kilovolts to be able to make this intrinsic region, which is the region where it's actually sensitive to the incoming radiation, as large as possible. So if we have a gamma ray photon coming in there now, it knocks away one primary electron, by, let's say, for example, photoelectric effect or Compton scattering. That electron might ionize then several secondary electrons. In the end, we have quite a lot of charges which are free here. Because of the electric field we've set up with a high voltage, we'll have the electrons kind of moving towards the contact that we have the positive part of the high voltage on, whereas the holes that are left behind by the missing electrons kind of will, in effect, travel towards the negatively charged P contact. So the P contact, of course, P stands for positive, but we have the reverse high voltage here. So this will basically create a change in our electric field, which we can register. So the output is some kind of electrical signal. And indeed, there is a proportionality here, which is very important. The absorbed energy here from the gamma ray photon is then proportional to the electrical signal that we get out. It depends on how many secondary electrons are created here. So this proportionality is very important because that allows us then later to know which energy was actually deposited in our detector by the gamma ray photon. So that's basically the detection principle. And the different kinds of configurations that we've seen on different kind of crystals, they might have different applications in terms of how sensitive they are to a gamma ray photon emitted by or actually interacting with the detector emitted by the sample at a certain energy. So low energy photons will tend to be absorbed quite quickly statistically. Higher energy will tend to travel larger distances. So you get this kind of efficiency curves. You see that N-type detectors, which is kind of this curve number 1 here, has a better efficiency at low energies than the P-type detector, which is this kind of number 4 here. There's a lot of different configurations, and in the end, when you choose a detector for your application in your laboratory, it's a good idea to think about what is my application, which energies am I looking at, and where do I want the detector to be really sensitive. Detector efficiency is a big subject. We will actually talk about that more in webinar session 3. All I want you to know now is that different types of detector crystals will have different efficiencies at different energies depending on their shape, how the contacts are, how the end cap window is, and so on. And we will go much more into detail about that in the 3rd webinar session. But at least we know now what means detector efficiency. And this is something generally, of course, that you would like to have a high probability to detect a certain energy of emitted gamma ray in your detector. So this kind of detector and the way it works requires us, of course, this, it's quite a comprehensive process. And in order for it to work properly without a lot of noise and so on, we need to cool our detector down to cryogenic temperatures, less than, let's say, minus 170 something degrees centigrade. That's what they need to function properly. Traditionally, this was always done using liquid nitrogen, which has usually keeping around the boiling point of minus 196 degrees Celsius. So liquid nitrogen was chosen because it kind of matched up rather well with the ideal temperature for a germanium detector. Nowadays, what you'll see more and more is different kinds of electrical cooling mechanisms where you don't have to refill your liquid nitrogen every so often. You just keep it plugged in over time, and then eventually maybe you have to change out some mechanical parts, though a lot of development is happening on that field as well to make it less and less work intensive to keep them. What's also come in the last, let's say, 5-10 years is this hybrid coolings where you have a nitrogen in a tank, and then the top part is a system to regenerate that nitrogen using a cooling technology. So you recycle the liquid nitrogen, and basically in the end you fill it once, and then maybe a year or two after you need to fill it again because it slows down the process, compared to maybe filling every week or so with these typical nitrogen dewars. If we kind of look at the anatomy of a nitrogen cool detector, again, a cross-sectional view might look something like this. You have your detector crystal here mounted inside the end cap, usually connected to some kind of a preamplifier, and then the whole thing here has a long kind of cooling rod with a cold finger at the end, which is used to kind of keep it cold by keeping it in contact with the liquid nitrogen, which is inside this dewar here. That's basically how the main setup might look. If you have a typical traditional nitrogen cool detector, chances are it looks quite similar to this. Now, this being very sensitive equipment, of course, it's sensitive to all radiation, not just what's coming from the sample. So stuff which is already present in the background environment, such as in the counting laboratory room, for example, you would like to keep that radiation away from your spectrum. And that's why you usually have some kind of a shielding around the sensitive part, the actual detector crystal inside here. Usually that's some kind of cylindrical or kind of square thing consisting of lead having a very high atomic number, high density, very good to attenuate away the photons coming from outside. And usually you have around 10 centimeters or more of lead. Often you'll also have on the inside of the lead kind of tin and copper or cadmium and copper to take away the X-rays from the lead. And in the end you'll kind of optimize, and you'll see here kind of on the right side, maybe a typical spectrum, how might the spectrum of a detector look if you just measure the background without shielding and with shielding, and you see we reduce by few orders of magnitude really the background noise to the detector. So this is really noise that you don't want to have in your spectrum so much. So that's kind of some things you might have around your detector to keep it happy, so cold and low background. Then of course the charge signal from the detector, the electrical signal, is processed through some electronics, as we showed, and this happens through a preamplifier and usually like a main amplifier, which are not only amplifiers, indeed they also convert the signal to a voltage pulse, which is easier to send through cables. They reshape it into a shape which makes it easier to get a nice peak height reading from that. They amplify it to make it larger, to optimize the kind of signal to noise through the cables. Here's an example, if you look on an oscilloscope, of the voltage pulses from a preamplifier and from a main amplifier, how that might look. I will not go through so much in detail about this. Again, I think there are many resources out there if you're interested in this part, but for the interest of time, I'll just leave it at that. And what we have, kind of the important thing here, is that the pulse amplitude of these pulses, so that the height is proportional again to the energy. So we can process our energy signal through the system and get out the signal at the other side, which is proportional to our originally deposited energy in the detector. Important. These are kind of voltage pulses, nice to look at, maybe not so nice for a computer to analyze. So what you'll usually have is some kind of analog to digital conversion happening in your electronics. So this is basically converting the pulse from the amplifier, so the light blue pulse on the previous slide, into some kind of a number that can be digitally sorted later on by the MCA. We'll see that on the next slide. This is also where you can kind of put limits on which pulses am I actually interested in. Certain height of the incoming pulses you might want to keep, and those that are outside this range you might want to reject. So here's kind of a typical example of a rejection where I'm only interested in all the voltage pulses from the amplifier with heights between H1 and H2, and all the other ones which are either too big or too small for that I reject and I don't process further. This can be a typical way of reducing kind of the noise in your spectrum by discriminating away low energy noise, for example. Now we have some digitally converted pulse height data, and those are then sorted into a spectrum. So we can imagine there's like a guy sitting and counting each incoming event to our detector, like we see in the picture on the left side. That would go maybe too slow compared to how fast the detector is working. But basically, pulse with a large amplitude will be sorted higher up in our spectrum than a pulse with a low amplitude. Again, we're skipping here the kind of analog to digital conversion. It's sorted into a predefined number of channels. In our histogram here, that is our spectrum, and that we can then later on relate to the photon energy of the incoming radiation by this kind of proportionality that is kept throughout the whole signal processing process. So the spectrum is then simply kind of a histogram of energy signals that have been sorted according to their amplitudes or heights into the appropriate channels. And of course, once we measure over time and for long enough, we'll start to see these characteristic effects in the spectrum, such as the peaks. But yeah, this is basically what the spectrum is. The plot of counts versus energy as sorted events from energies deposited in our detector. Summarizing this whole signal processing as an example here, we can say that we have a source or sample that emits a gamma ray. We get an electrical signal out because of the high voltage we put over our detector here. There's an electrical signal here. Might go through the preamplifier, create a pulse there, then sent to the main amplifier, which creates a pulse with a much nicer shape, converted from analog to digital by our ADC, then sorted by our multi-channel analyzer, eventually into a spectrum. So there's a lot of kind of electronics, digital processing, analog processing of signals happening here. Traditionally, this was done with the so-called nuclear instrument modules, the NIM standard that was called. And you might go into the counting room and you might see a cabinet full of modules and cables and chaos looking something like this. Nowadays, you have this much more streamlined looking digital analyzers, which are all in one. They do the amplification, they do the analog to digital, they do the sorting of pulses, they provide even the high voltage, they have built-in functionalities for a lot of things. Even now, you can have digital signals coming directly out from preamplifiers. So we're moving digitally in this world as well, like with other, like with a lot of things in this world. So this is kind of how the electronics might look. And then once you have a spectrum coming out from either your analog electronics or your digital electronics, you need a computer then with a kind of associated software to control maybe when you start and stop your measurement, but also maybe very importantly to do the analysis. And there's a lot of softwares on the market. Here are some screenshots from some of the software that I know about. Probably there's even more that I don't know about. Generally, you'll be kind of forced in the direction of a certain software depending on which manufacturer you have your detector and your electronics. But there are many softwares available. Yeah, I'm not going to discuss so much more about that. There are disadvantages and advantages of every software. And I think in the end, maybe you can do good things with any kind of software if you know exactly what you are doing. And that brings me maybe to the most important component of this whole measurement system, the analyst. So again, that could be you guys or your colleagues. And I will go so far as to say that the whole measurement process is more or less useless without a skilled person to interpret the results and ensure that everything is running correctly and in the end maybe report the results in a usable and informative way. So I think a lot of gratitude should also be given to the people who are in this field for kind of the large part that they put in to make sure that the results we get from this technique is correct. I would like to introduce one more kind of technical concept to you, and that is the concept of the energy calibration. So we talked a lot about now that the multi-channel analyzer sorts each event into a channel in the spectrum, and there's like a total number of channels available in the spectrum, which is usually between, let's say, 512 or 16,184 or 8,192. The reason why these are not round numbers is generally because these are powers of 2. So, of course, what the MCA is doing is it's sorting and making our spectrum into channels. And you have counts here on the y-axis, and we see here some peaks. Of course, if we just look at the channels, it's not so useful because we would like to know the energies of these peaks, because that's the information that will allow us to identify these nuclides. And that's when we need to do some conversion, some kind of energy calibration to convert channels into energy. So you see now actually the channels changed into energies here on our x-axis. And now we can see, oh, there's a peak at around, 650, 700 kilo electron volts. Might be cesium-137, for example. And the way you do this is by so-called energy calibration. And this is something you do by measurement of known sources to relate the channel number to a certain photon energy. So you'll measure sources that you know, or samples that you know the energy emissions of. You'll measure, for example, americium-241, which sends out gamma at 60 keV. You'll see that, okay, 60 keV gives me a peak in this channel here. Maybe you'll measure then potassium-40, another common nuclide, which gives you a signal at 1461 keV. You see, okay, I know I have this energy. It gave me a signal here. Very nice. Eventually, you might draw a curve through those to get a general relationship between channel and energy. And of course, when you choose the total number of channels available, and when you choose kind of approximately which channel do I want to see the certain type of peak is, that depends on which energy range are you looking at for your measurements, and you can make adjustments to your electronics to make sure that the full range of your spectrum covers the energy range that you are interested in your measurements. So once you have this curve here, of course, it's easy then to fit this with some kind of a formula. This is a very simple straight line formula which relates the energy to the channel number in the spectrum, and there's some parameters A and B depending on the slope and the intercept of the line, which are then fitted experimentally using your measurement data. And then once you establish this curve, you can use it to predict the energy of a peak appearing in basically any channels. If you have something here, you can say, oh, it's this energy here, and I know that's this nuclide. We did this example very simply. You might say, okay, you can fit a straight line to any 2 points. Does it make sense? I didn't do this, but you'll find examples of people having done these kind of energy calibrations using many energies. This, I think, is a lot of energies coming from europium-152, which kind of proves that even if you decide to use a lot of points to plot your straight line or to fit your straight line, this straight line hypothesis for the energy calibration is indeed true. So So that's the energy calibration to relate the channel number of the spectrum to the photon energy of the registered radiation. So we're coming slowly towards the end, and I would like to finish off the lecture part with going through maybe what the typical process, what is kind of the typical measurement process that you might have in a typical Almera lab maybe when you're looking at environmental radioactivity monitoring. And usually the first thing you need to do is to define what is your sample. And often if you're in the laboratory measurement field, you start by kind of taking a sample from somewhere. In this figure you'll see that there's some soil that they are taking from some kind of a grassy site, and they're going to take that back to the laboratory. So it all starts with kind of sampling what you want to measure. In other cases, for the in situ measurements as we saw originally, it might be taking the detector into the field. But in this picture, I decided to show you taking a sample to bring it later to the lab. And what might be typical sample materials? So these are some kind of typical types of environmental samples. So there might be some things such as water, soil, plants, even food products, maybe not sampled from a grassy field, or maybe could be, but maybe could be taken from a supermarket. Could also be such things as building materials, air filters, industrial waste products, and many, many more, I have to say. Basically, this is a very general technique. It's non-destructive. You take your sample, you put it, you can measure on the sample in almost any shape or form that it has. You get simultaneous detection of all these different nuclides by the gamma spectrum in all kinds of different materials, really. Of course, if you want to do a precise measurement, you would probably like to process your sample a little bit, such as crushing it, sieving it, drying it, taking out kind of rocks or stuff which you're not interested in, and eventually preparing it into a suitable measurement container. Since this is physics, we usually like to use cylinders because they're easy to deal with mathematically also. But you have kind of cylindrical containers. You can also have these so-called Marinelli containers where you fit them on top of your detector like a glove, and you have your sample surrounding your detector, also very commonly used. So yeah, you would kind of prepare your sample and make it ready for your measurements. And then once that is done, you would measure it on hopefully a calibrated and well-adjusted detector for a specified length of time, and then you obtain this kind of gamma spectrum eventually, which you can then analyze further. And again, I think really we talked about this so many times. In the spectrum, you then look at the location of the peaks in terms of their energies for the identification of the nuclides, and then you look at the areas to use for the activity calculations. Once you have a spectrum, there's quite like a process to go about how do you actually analyze that on a computer with a spectrum analysis software. This is kind of how a typical process for that might go, by peak search, peak area determination, and so on and so forth, all the way till you get kind of results that you can report. This slide is exactly kind of the content of the next webinar, which I believe will be on the 7th of April. So if you're interested in this part of the job, be sure to tune into that or access the recording later on, because we'll discuss all these steps in more detail there. So once you have some results from that, you would generally not maybe trust the software just blindly and report whatever it tells you. You would maybe check it by a skilled operator and report it in kind of a useful format that can be understood by the person who requested the analysis, by doing it in kind of a clear and unambiguous format where there's no doubt as to, okay, which sample has which nuclides at which levels. And hopefully whoever requested that might be a person in your laboratory, might be an external customer whatsoever, might really be a person who doesn't have so much experience in the field. So it's really important that you report the results kind of in a good way to not be misunderstood. But that's usually kind of what you will do at the end of the process to report your results that you achieved. Of course, in addition to this process, there's a lot of other pieces of the puzzle. Having procedures to do what you're doing in a standard way, calibration of the equipment, validating your methods, using suitable nuclide libraries for calculations, participating in proficiency tests to make sure that your results are on a good level and comparable to other laboratories worldwide, performing quality control to make sure that your equipment is working properly, and if it's not, or even just in general, making sure your equipment is maintained properly. Probably more things also that I've not listed here, but there are many pieces to this puzzle. But I will just mention them and not go into so much detail. So that actually concludes it for the main part of the lecture. Before I go to see if there's any questions to answer, I just want to give a couple of pieces of practical information. So I've made a kind of document with a few homework exercises. If you're interested in what we were talking about today, but would maybe like to try it out in practice, these are basic exercises for basics of gamma ray spectrometry. Should hopefully be possible for anyone to do. They don't require any software. They are kind of pen and paper exercises. Maybe you would like to have like a small calculator or something, but otherwise they can really be done without any special software or so. You can print that, and there's even space to like fill in the answers on the pages if you prefer to kind of do it kind of sitting at the desk and focused above that. For now, only the exercises are there. I will publish the solutions exactly 2 weeks from today, so everyone will have plenty of time to do it. Probably, if you know what you're doing, you can do it very fast, but in case someone doesn't have a chance to even look at them for some time, I will publish the solutions on the same link in the same Dropbox folder 2 weeks from today, Wednesday, 24th of March, so you can see how you did and hopefully verify that your answers correspond to kind of the solutions there. We do have 2 more webinars planned in this series. This is just taken from the invitation, which I hope most of you have received. The next one is on Wednesday, the 7th of April, and it's all about gamma spectrum analysis and activity calculations. We'll go a little bit more into the details about that, a little bit more into maybe some mathematics of it also, but hopefully not so complex that we lose everyone. But that will be the topic of the next one. And then 4 weeks after that, on the 5th of May, we will go through a topic which I know many people want to know about how they can do. This will be all about efficiency calibration of high purity germanium detectors. And we will focus on high purity germanium detectors used in the lab, in laboratory settings for that one. It's still possible to register for those. And you can use this SurveyMonkey registration form to register if you have not already done so. If you have done so, then don't worry, you will get the email with the WebEx link after we close the registration to connect like you did today. And we will aim to close the registration around 2 days before each webinar takes place. I know for this one there were some kind of late applicants also, and I hope I managed to catch some of those and send the link kind of yesterday evening or this morning. But for our organization, we will appreciate to kind of have the final list of registered people 2 days before a certain webinar. Again, if you've already registered for the next webinars, no need to do anything. You will receive the email. Don't worry about that. Final thing I would like to say is that at the end of this month, so that means before the next webinar, we will go into something called daylight savings time here in Austria. And that means we adjust our clocks 1 hour forward in the night. So 2 a.m. will suddenly become 3 a.m. Unfortunately, we will lose 1 hour of sleep, but such is life. So I think for everyone joining from Europe, you're probably doing the same thing. So the time difference will be the same, but those of you joining from other parts of the world, especially those of you who don't observe daylight savings time, please note that actually the time difference you had for today's session might be different for the next session, which will be in April after we do this. So please check when you get the meeting invitation that you are joining at the right time. And with that, I would like to thank you for your attention, and I will see if there's any questions. And if you are leaving us at this time, I would like to say thank you so much for joining. It was really nice to have you here. If you're watching this as a recording, thank you for watching the recording. I hope to see as many people as possible at the next session. Hopefully it was useful, and you found it interesting. We will upload the recording also to the Dropbox. I guess it depends. It can take a day or two because we need to process the video or so. But if you check back in there in a couple of days, the recording will be there. Feel free to share that with anyone you know who might have an interest to see this, but wasn't able to join now. And yeah, thanks. So let's see if I can see if there's any questions. Okay, so I think I found the Q&A panel, but actually a lot of them are about the kind of technical thing about the webinar. Yes, we will share everything. Everything is being recorded. You will have everything. It will be shared. You can watch it again. Pause if you need to look more at a certain slide. You have the slides also to look directly at that. So I will not answer so much the kind of more technical questions about that. I'll answer more the ones which are on the topic of gamma ray spectrometry. So I have a question here which says, there's a question from Mai Wo Yi that says, why do I sometimes see a tiny peak at cesium-137 location when counting routine background sample? Which nuclide could be interfering? Thanks. So, of course, I haven't seen your detector, and I don't know exactly how the spectrum looks, but I can tell you that actually seeing a tiny peak at that energy is in many parts of the world not at all unusual. Cesium-137 is one of the most prevalent anthropogenic radionuclides in the world today. With its 30-year half-life, it's it's still present from kind of Chernobyl releases, Fukushima releases, nuclear test explosions, and so on. It could be that in the environment of your detector, there is just a tiny bit of cesium. I know we sometimes, I've seen sometimes on other detectors that effect. I can't think immediately of another nuclide which would just put a peak there in your background spectrum without it actually being cesium. That being said, if it's a tiny peak and you know about it and you subtract it, you should be able to deal with it. So I have another one from Michael Davidson. Can you say something more about the difference in performance of P-type and N-type detectors? Yes, I can. So we went through very fast the different types of detectors because in the interest of time, I didn't want to, you can really spend a lot of time on that. But I'm happy to tell you some of the differences in performance as I've seen it. So P-type and N-type refer to kind of the material of the detector. So we talked about it's this intrinsic germanium crystal, but actually if we have 100% perfect crystal, then it would be boring because we wouldn't really be able to get a good electrical signal from that. So the P-type and N-type detector materials are slightly doped with either a kind of a material which has a little bit more electrons around in the outer shell, or a little bit less to make kind of the overall material slightly more electrons compared to the holes in the crystal lattice, or slightly less electrons compared to the number of holes. And basically, in terms of performance, N-type detectors, traditional N-type coaxial detectors, they have the positively implanted contact on the outside of the detector. What you will usually see, what you will usually be facing your sample. So that means that the gamma rays from your sample have a shorter distance of contact to pass through before they can actually reach the sensitive detector material. So that's, first of all, a good thing at low energies. Because more low energy photons will be able to be transmitted and not absorbed in kind of this dead layer on top of the crystal, like on a p-type. On the downside, since the N contact is on the inside of the detector, electrons that are knocked loose kind of towards the detector surface. So if you have your sample on top of the detector, and it's emitting gamma rays down towards your detector, low energy photons will tend to interact kind of in the top few millimeters or few centimeters and deposit their energy there. Those electrons that are produced will have a longer distance to travel to reach the N contact, which is connected to the positive high voltage. And as a result, it will have a little bit poorer charge collection, and you'll see actually that the resolution at low energies of N-type detectors is a little bit worse. So I spent a lot of time to answer a simple question, but basically N-type detectors generally have a bit higher efficiency at lower energies, but also a little bit worse resolution at low energies. P-type detectors traditionally also can be made larger than N-type detectors. The price is generally lower. Nowadays, you can even get P-type detectors, which have kind of mechanically reduced the thickness of the front dead layer. So you don't really have this poorer efficiency at low energies. Those are called extended range detectors. But yeah, I hope that answers a little bit your questions at least. Here's one. I have a question. How the yield of gamma ray energy emitted by a radionuclide is calculated? From Maria Angela Menezes. I assume you refer to here kind of the probability that a nuclear decay will emit a gamma ray at a certain energy, so the intensity or emission probability. This is huge work basically to determine these probabilities, which are done by meteorological research institutes, and they basically use various measurement techniques with extremely precise calibrations to measure sources of the radionuclide of interest and look at the relative emissions at different energies. Then they try to put that into the form of the decay scheme and make sure that kind of all the probabilities match up so that the probability of decay to an energy level matches the probability of decay from that energy level again to balance out the budget. I'm actually not such an expert in that field, so I hope I didn't say anything wrong right there, but I know it's extremely complex, and I think these kind of values, which you find in nuclear data tables, and you often take for granted, there's a huge amount of work behind those. So hats off to those who do that. So here's another question. Are there any differences of spectrum if we use different types of detectors, for example, coaxial and planar? So, of course, you shouldn't expect really to see other peaks from the different detector types. What you might see if you measure a certain sample on a coaxial detector compared to measuring that sample on a small planar detector is that the relative sizes of the peaks change. A planar detector generally is very good for measuring low energy photons, which anyways, if you have your sample at the top of the detector, would interact kind of in the top part. So no need to have kind of a long coaxial crystal behind that. However, higher energy photons might have an easier chance to just pass through that material without interacting. So you'll generally see, like, if you speak in terms of efficiency, you'll generally see like quite good efficiency at low energies, then it sharply drops off at the high energies. So you might see like the relative sizes of the peaks compared to each other are different. Another thing you might see for planar detectors is that the resolution is often very good at low energies. Again, this has to do with the way that the contacts, the P and N kind of contacts of the detector are configured compared to the crystal. Don't want to go into the details, but planar detectors will often then have very sharp resolution especially at low energy peaks. So you can have really small peak widths at low energies. Yeah, I think those are the main differences. I hope I didn't forget anything. So I'll move on to the next one. So here's a question from Anton Risti, and it says, are you going to discuss the ways uncertainty can be calculated in future webinars? And the answer is yes. We will discuss a bit about that at the next one, which is about spectrum analysis and activity calculation. Not in super detail, but it will certainly be mentioned because to report measurement results without any kind of uncertainty statement can be a little bit dangerous because you have no idea about how sure is that value then. So the answer, I guess, is yes. Yes, we will mention that during the next webinar. Then we have one from Takuyo Abe. I have one question about germanium crystals. Sorry, I can't see that whole question. I'll come back to that one. I'll jump to another one first. Maybe I'll come back to that one. This is from Roman Galev. Is there a reason why the signal typically has a negative polarity after the preamp, and then polarity is converted by main amplifier? So the signal from the preamplifier, if kind of the pulse drops below the baseline negatively, or if it goes above the baseline positively, that depends on whether you have the kind of normal p-type configuration crystal, or if you have an n-type crystal in which the polarity is switched of the high voltage. So I didn't mention that, but basically p-type crystals generally have high voltages of a few thousand kilovolts positive. N-type detectors usually have voltages of a few thousand kilovolt negative. And depending on the polarity of that, it will also make the preamplifier signal positive or negative. And that's why often when you are configuring your amplifier, you have to tell it, okay, this is a negative incoming signal or a positive incoming signal. Because if the amplifier is expecting a positive signal, but you have a negative signal coming from your preamplifier, then you will probably not get a very nice spectrum. Yeah, that's, I hope answers that question. Depends on, I wouldn't say it's typically, it depends on which detector you have. But for a certain type of detector, certainly, depending on if you apply a positive or negative high voltage, it will also affect then which polarity of the signal is coming out of your preamplifier. Here's a question from Mohammed Kourouch. Here's a question about the periodicity of background analysis. This is a great question. So basically what it's asking is that, okay, I want to know the background spectrum of my detector so that I can correct my measurements for it. How often should I do it? It's a great question, which is unfortunately not so super easy to answer with like one answer, because really it depends on your the conditions in your lab. Some people are very kind of adamant that they need to have a background subtraction which corresponds exactly to the time interval that the measurement is done. So if you're doing a measurement from, I don't know, Friday to Monday of a sample, then you also subtract the background from a Friday to Monday where the detector was counting with no sample present. I know a lot of people do it that way. Some people do it where they do a kind of long background measurements, and they subtract kind of an average background over a week from their measurements. Whether one or the other is correct depends a little bit what kind of variation you have. If your background is varying, it's different during the week than during the weekend, for example, then maybe this kind of specific interval backgrounds is good. If you don't have this kind of variation over time, maybe it's nicer to have a longer background measurement where you can catch maybe tiny peaks in the background that you can't see otherwise. About the periodicity, I don't have kind of a great answer for this. I can tell you what we do here. It's a little bit of insider information from our lab. We don't have background variation so much kind of during the week. So what we do is we do long background measurements twice per year, but then every month we follow it up with a background check. So we do a short kind of background quality control just to make sure that the general background hasn't gone up or down. So in the end, the kind of background monitoring frequency is every month. Some labs who do kind of much shorter measurements might want to shorten the period of the background measurement and rather check it more often. It really depends on the application. I think quite normal for environmental laboratories is maybe around once per month or so to do a screening of the background and then to consider whether you use this specific backgrounds for a certain time period, or if you do longer background measurements a few times per year for your background subtraction. So have you ever observed any variations of potassium-40 backgrounds in spectrums due to external environmental conditions? Personally, I have not really experienced that. Of course, we have slightly different area of our potassium peak from week to week, but we haven't been able to see any trends of that. Basically just what would be expected more or less from statistical variation. If you do observe that I find that's interesting. I haven't seen that, but it's interesting. And maybe if you're interested, you can send me a mail and we can discuss it a little bit more further, because it's something new to me. Here's one from Pierre Bouchereau de Pury. Probably said that wrong, but hopefully. What is the influence of the sample geometry on your spectrum? How far can it differ from the calibration source without affecting too much the results? Another really great question, and one I unfortunately don't want to spend so much time on now, because this question will exactly be one of the topics we will discuss in the webinar session 3. For the question, what is the influence? Answer is it depends, but it can be a lot. And of course, the effect it has is it's on the efficiency of detecting different photons. So generally, you won't see other peaks depending on the sample geometry, or you never will see any different peaks depending on the sample geometry, but you will see kind of different ratios of the peak areas, which are related to the difference in efficiency from different sample geometries. And how far can it differ without affecting the results? Well, it's a great question, and hopefully we can shed a little bit more light on that during the webinar session 3. Sorry to not spend more time on that now. I hope you accept the delay to keep you waiting there. So here's a question from Haruetai Kasiwatanawut. Good. If we would like to study one nuclide, should I do energy and efficiency calibration with a known source of that nuclide? So this goes into something which is kind of called direct calibration or direct comparison. It's a possible way of doing it. I would say energy calibration, it's so easy to do. I will recommend everyone to make a general energy calibration, so you really have the full picture of relationship between channel and energy. To do the comparison directly between kind of a standard with a certain nuclide and compare that to the sample of a certain nuclide, that is a very acceptable way of doing it, but you need to make sure that the sample and standard are kind of geometrically or physically the same, or at least very similar. If not, there could be geometric differences that would affect and create kind of an error that if you don't correct for it. So going on, there's a lot of questions. I will keep going a little bit longer. I see we're approaching the end time in a few minutes. If you do need to leave or want to leave, perfectly understandable. I will not hold it against anyone. But I'll try to stay here for a little bit longer to answer the last questions. But yeah, if you want to stay, perfect. If you want to go, totally fine as well. So the next question I have here is which kind of the detector would be more suitable for measuring high activity radionuclides, for example, those used in nuclear medicine? Good question. So nuclear medicine is not my field, I have to admit. From my immediate thought, when you come into like high count rate applications, you definitely don't, it's definitely no longer the case then of bigger crystal is better, because actually with bigger crystal comes also where you might get like high dead time or something like that. So I would think that the best detector is maybe a smaller detector, and on the type of detector it depends on what is the high count rate application. For nuclear medicine, where I would presume, without knowing the field too well, that there is not so much neutrons going about, maybe a smaller p-type detector would be sufficient. However, if you're in the nuclear field and like a nuclear reactor or something, and there's the risk of neutrons being around as well, then I definitely recommend N-type, because N-type detectors are much more resistant to so-called neutron damage, which can really be a huge bother for P-type detectors. Which I guess kind of goes back to the original question, to a previous question about the performance differences between P-type and N-type. Forgot to mention that N-type detectors are better choice if you are using it in somewhere where there's a chance of a neutron flux hitting your detector. Furthermore, for high activity, high count rate applications, I recommend to not have the sample so close to the detector, maybe move it a little bit away, because it will give less summing and less need for correction for summing, while the activity is still probably high enough that you get enough of a spectrum without having to measure so long. Here's a question from Hassan Unlu. To what extent can the dead layer of an high purity germanium detector increase? Does it only depend on time? How about temperature and usage effects? So we mentioned the dead layer very briefly. So the dead layer, what we mean is this kind of layer, typically we did talk about it for p-type detectors, this outer N plus layer on the outside of the crystal, which is a dead layer, because if the photons interact there, we don't get any signal to our detector. Now for p-type detectors, that is true. With the process that those dead layers are made, there's a chance that if the germanium detector is kept warm for a long period of time, that dead layer might grow, increase in thickness, effectively kind of increasing the dead layer means reducing a little bit the sensitive part of the crystal, especially then for low energies, which will generally interact kind of closer to the top where the dead layer is then. I'm not aware of any specific extent, but I do know that what it depends on is keeping it warm, keeping the detector warm over a longer period of time, but the changes kind of dampen. So if you keep it warm, the dead layer can grow, but eventually it will kind of slow down this growth of the dead layer. It's not like the dead layer will take over your entire crystal if you kept your detector in storage. What you might have if you calibrated your detector and then you kept it warm and then you kind of recooled it and wanted to use it, you might see your efficiencies at low energies have decreased, unfortunately. That's kind of, might warrant a recalibration or a correction for that. But yeah, the safe option is to keep your detector cool, of course, but I know for some labs it's not possible. Yeah, it depends on keeping it warm, and it depends on keeping it warm for a longer period of time. Okay, so I try to go to some of the last questions here. We have a handful of questions. Just a couple of questions left. It's 11 o'clock. This was the promised time. I'll stay for another 5 or 10 minutes just to answer the last ones. Yeah. So we have.
So there is still the question from Takuya Abe.
Yeah.
Waiting, and I can read it out. I have one question about germanium crystal. Are the crystal of P-type coaxial detector and that of well-type detector essentially the same?
It's a good question. There are a lot of similarities, and of course, from the figure, they look very much the same. Generally, it's similar, but the contact can be quite different because of the way kind of the one contact is on the inside of the well and the way that is configured. What you will see as an effect of that generally is that the resolution of a traditional well-type detector will be worse. And yeah, if that makes it different, then essentially the same. Who knows? You can make well-type also N-type. It's also possible. Nowadays, there's even like new type of well-type detectors that are called like SAGE detectors. So they call like small anode germanium, SAGE, and they have like a different contact configuration, which has like better has a kind of better resolution, even at the energies which would have bad resolution on a well-type detector, while still keeping that well in the detector. Yeah, it's not as easy as just opening your detector switch, flipping it on its head, and putting the sample inside. There are some other things as well that are a little bit different. So. Okay, so I see one more question which just came in from Amina Al-Abduli about whether or not the cooling method affects the measurement results. So cooling method, we mentioned we have the liquid nitrogen, cryocycle, electrical cooling. Of course, these are all methods of bringing the temperature of your detector down. In terms of affecting the measurement results, I will take one step back and talk about affecting the spectrum, because what you might have, especially with the older types of electrical coolers, which kind of had electrical compressors, they made some noise, there was some vibration. The germanium detector, being very sensitive, would then pick up that noise, and that noise would propagate through the signal processing chain and kind of worsen a bit the resolution of the full energy peaks, especially towards the low energies, where the relative contribution to the resolution is kind of more affected by this kind of electrical noise. So what you would see then with the kind of first types of electrical coolers and also the early types of the kind of hybrid cooling systems like the cryocycle, Möbius, which recycle the nitrogen, is that you would sometimes see worsening of the resolution for your low energy peaks in the spectrum. Not a lot, but maybe certainly by like 10-20% relative. So instead of like, I don't know, 1 keV resolution at 100 keV, you might have 1.2, something like that. In terms of affecting the measurement result, I guess as long as you are aware about the shape of your peaks at different energies and your software is aware about that, that shouldn't have affected your measurement results so much in terms of like the activity value you get out. But I know some people were bothered a little bit by this worsening of the resolution, especially at low energies. Sometimes it could happen that kind of as the compressor was getting old, really a lot of noise came and it would start to really put a lot of counts in the low energy part of your spectrum, like making noise for your low energy peaks and so on. That was usually then a sign that the cooling system was dying, and it's a time to maybe call the company and schedule a service. But otherwise, I haven't seen like great difference in kind of the accuracy of measurement results. And I have heard that the newer generations of cooling systems, both in terms of purely electrical cooling, also in terms of the later generations nitrogen recycling systems, they have kind of implemented new technologies where the noise that is generated is less. So I hope that answers that. I personally wouldn't be hesitant now to choose an electrically cooled detector, whereas maybe 10-15 years ago you would think, oh, but maybe it's better resolution to go with nitrogen. Now those differences are getting so small that it's practically the same. I think that kind of covers the questions we have. Alex, have you seen any questions now that I haven't answered?
No, I think I did not see any further questions.
So I'll stop sharing, so you'll see my face a little bit bigger then maybe. So in this case, I think thanks a lot for everyone who joined. I see we still have around 240 names here on the list. We even went now 7 minutes over time. That's really nice to see. You'll find the files on the Dropbox, later on also the recording, in 2 weeks the solutions to the exercises. I hope as many of you as possible will tune in 4 weeks from now for the next session. Hopefully maybe some of the questions you had will also be answered in part then. So I look forward to see as many as possible of you then. Still possible to register. Feel free to share everything with colleagues of yours who are interested in this field. I think one of the most important things about this is to spread knowledge, so don't feel the need to ask permission, just go ahead. And otherwise, I wish you really all the best wherever you are in the world. And yeah, see you in 4 weeks. Bye-bye.